Hey, welcome back to Math with Patrick. Today is September 25th, and we're solving problem 268 from the Daily Epsilon calendar. And the answer today should be 25 because the answer always matches today's date. So we need to find the sum of the squares of all complex solutions to this equation right here. And the reason why this is a z is z usually indicates some kind of complex number rather than a real number. Like usually if we had like an x, that implies that we're anywhere between like negative infinity and infinity. But then just kind of by convention, if we use the variable z, we have some kind of complex number that has a real part and an imaginary part. And so we need to figure out what complex values of z cause this equation to be true. So we could just try it out using algebra steps first, I think. We have z minus 4 to the fourth equals z minus 2 to the fourth. I think what would be the most straightforward is just to subtract one of these terms to the other side. So I'll subtract that z minus 2 to the fourth to the left, and I have this equals 0. And this right here is actually a difference of squares. If you have like a squared minus b squared, and we could just say it's equal to 0 because that's what we have in this current problem, you can factor this as a plus b times a minus b. All the distribution essentially boils down to just this. So if I can identify what a and b could be in this scenario, then I'll have a factored form. And usually the factored form is easier to find answers with when you have something equal 0. So if a squared is equal to this, then I think a itself will have the power of 2 on it. Something like z minus 4 squared plus z minus 2 squared, I think is going to work for my first factor. And then for my second factor, I'll have the exact same thing, but with a minus sign in the middle. So z minus 4 squared minus z minus 2 squared, and this is still all equal to 0. And so interestingly, I have yet another difference of squares on the right side here, because like this is a square number and I'm subtracting another square number. So I can use the exact same factoring strategy to factor that one further. And again, more factors means an easier time finding solutions to this kind of quartic equation. So I'll keep the left-hand side kind of open for a sec. I think I also want to do something to that in a bit. But at least over here, I can factor this as a plus b, and then times a minus b. Cool. And then over here, there is no like factoring strategy for the sum of squares. So I think on this one, I could expand it out just to get it in some kind of standard form. This will end up being a quadratic because we just have something squared and then adding it together. Expanding out the first one, we get z squared minus 8z plus 16. Expanding out the second one, we have z squared minus 4z plus 4. So combining like terms, we have 2z squared minus 12z plus 20. Cool. So I have a factor here, I have a factor here, and I have a factor here. And you know what? Maybe we could actually simplify the second and third factors a bit, because it looks like we can kind of collect up our like terms. So we'll keep the 2z squared minus 12z plus 20 the same. Here, it looks like I have z minus 4 plus z minus 2. So overall, I have two z's here, and then I have a minus 4 and a minus 2, which could be a minus 6. And then here I have z minus z, so those z's cancel out. And then I have negative 4 minus negative 2. So overall, this factor is just the number negative 2. So in here, we can find some solutions by setting each of these three factors equal to 0. Because if we have a product of any amount of things and it's equal to 0, well then surely one, or at least one, of the original factors has to be a 0. Clearly that's not 0, so we're not getting our 0 out of that one. But we could set 2z minus 6 equal to 0. If we plug in a 3, this equation is true. And so z equals 3 is our first potential solution. Scrolling back up, we need to find the sum of the squares of all complex solutions. Unfortunately, all real numbers are also complex numbers. I said earlier that like a complex number has like a real part and an imaginary part, and it's totally fine if the imaginary part is just equal to 0. So this number 3 is the same number 3 that every elementary school student also knows. It just happens to also be classified as a complex number. So we're going to square this one just because the problem says so, and we will keep 9 in mind for later because we will need to find the sum of all the squares. So we'll just add 9 to whatever we get from this one. So let's see, 2z squared minus 12z plus 20 could also be our 0 because 0 times whatever is still 0. And I think for this one, the easiest thing for me to do would be divide by 2 on both sides, just to kind of simplify our coefficients and our constants. And then I could either do like a completing the square thing on this guy or the quadratic formula. And I think actually I might prefer completing the square because I know that if this were the number 9, I'd get a complete square. So we could like subtract 1 on both sides. We get z squared minus 6z plus 9 equals negative 1. This is just z minus 3 squared equals negative 1. And normally this never happens because normally with real numbers, when we square them, we always get a non-negative output. But if we're working with complex numbers, we totally can get a non-negative, or we can get a negative output here. Essentially, z minus 3 must be equal to I, because if we square I, just by definition, we get negative 1. The z minus 3 could have also been negative I, because the same thing happens with kind of this negative times negative as we would find with real numbers, where if you do a negative times a negative, it's basically a positive. So this is equal to just doing I times I, and then I squared by definition is equal to negative 1. So we have two solutions here. Either z is equal to 3 plus I, or z is equal to 3 minus I. And I suppose we should square both of these solutions and then add those with the 9 that we found earlier. So squaring this one, we get 9 plus 6i plus I squared. And then, I squared is, again, negative 1. So overall, this is 8 plus 6i. And then for this z squared, we get 9 minus 6i plus I squared. And then this I squared and this 9 can also become an 8 together over here. So if we add this squared solution, and that squared solution, it's basically just doing 8 plus 9, because this positive 6i and that minus 6i will cancel each other out. And so overall, we do get 25 for today. Cool. So there is the solution. Basically, we're all done. Although there's one more thing I want to show, and it's how to think about this graphically. I just feel like I want to talk about complex or powers of complex numbers just a little bit more. So let's see how we can solve this in a more graphical way. Well, this is the equation that we're starting with, and we need to put some kind of complex number here and here, the same one. After subtracting it by 4 and subtracting it by 2, we are going to get two different complex numbers now. But then after raising both sides to the power of 4, suddenly they're equal to each other again. So I do want to make a little analogy with the real numbers and show you that it does make sense that we might start out with two different numbers, and then once we raise them both to the power of 4, we get the same number. So this can totally happen with real numbers, as long as the absolute value of these two is the same. Like if I change this to a negative 3, there's going to be no chance that I do get the same answer in the end. These two numbers need the same kind of relative size or distance from 0. And the same thing is going to happen with these complex numbers here. I need both of them to have the same distance from 0. Or with complex numbers, this is called their modulus. We can think about complex numbers as just points in the plane, kind of like this. Normally, the x component is just kind of thought to be the real component of the complex number, and then the y component represents the imaginary component of the complex number. So doing something like this, where the x component is 3 and the y component is 2, this represents the complex number 3 plus 2i. And then to find its modulus, or distance from 0, you would just use the Pythagorean theorem here. So it would just be the square root of 9 plus 4, or root 13. And so we need to think about this first, trying to make sure that z minus 4 and z minus 2 have the same size, or distance from 0, or modulus. And I think it would help if we just replace z with a plus bi. This is just kind of that general form of complex numbers, where a and b are some real number, and this I makes this bi part imaginary. So this minus 4 doesn't have any imaginary component attached to it, so really we're just subtracting the 4 from that a value, and then the bi just kind of stays the same. Same thing over here. This minus 2 would only affect the real value of my complex number, not the imaginary part. So we could just move that minus 2 over here. And so both of these should have the same distance from 0 if we have any hope of these two things actually being equal to each other. And so if the imaginary part is equal to each other, then that must mean that the real part also needs to be equal to each other. Or rather, that they have the same absolute value, right? Because maybe I could have a point up here whose modulus is root 13, or I could stick it down here and it's root 13, or I could move it over here and it's still root 13, or over here and it's root 13. But at least with this setup, I can just see right now that the imaginary component's equal. So that's either the case that the real component is equal, or maybe they're like negatives of each other. So assuming that they're equal is a little nonsensical, because once we subtract a from both sides, we get negative 4 equals negative 2, and that's just not true. So the only other case that we could check is if the real component has kind of opposites here and here. And we could solve for a by like maybe distributing that negative, adding that a to the other side, and then adding this 4 to the other side, and I guess dividing by 2. That just shows that a has to be 3 for this problem to even have a hope of having a solution. So I guess I could replace that with a 3 and that with a 3. So I guess this is now negative 1. And I could replace this with a 3. So this is now the number 1. And it looks like our solution is now forced to have a real component of 3 no matter what. And you know what? Let's also get these other 2 points on the graph as well. Because once we take this point and subtract 4, that's like us having the point negative 1 comma b. And then if we subtract 2, that's going to give us positive 1 comma b. And I'll just make these the same color. Cool. So now we know that we have to have a real component of 3. And after raising both of these complex numbers to the power of 4, they're going to have the same modulus in the end. Another component that we do need to think about is like where they end up relative to 0, essentially what angle they make with the x-axis. And that's called the argument of a complex number. It's just this angle between the x-axis and rotating counterclockwise up to our complex number. And we can use another thing called de Moivre's theorem. It's a French name, de Moivre's theorem. And basically, this theorem states that when you do powers of complex numbers, the argument just kind of adds to itself each time you raise it to the next highest power. So currently, I have some angle that goes from the x-axis to here. And this is kind of the power of 1 of this complex number because it's just itself. And then if I squared this complex number, the resulting angle would be roughly, actually kind of near this one, I suppose, because I'm trying to add this angle to itself again. So I'll be somewhere in the second quadrant just based on de Moivre's theorem. And maybe let's just try it out to see what happens. This complex number would be 1 for the real component and then 2i for the imaginary component. And hopefully we're going to get some kind of result that lands in the second quadrant over here. And maybe that'll be enough proof that de Moivre's theorem does work with this kind of idea of rotations. So we could expand this one. That's going to be 1 plus 4i minus 4i squared. No, plus 4i squared. I squared is the same thing as -1. This turns into a -4, and then this -4 and this +1 produce a -3. So the result of squaring this complex number brings us to a real component of 4 and an imaginary component of, a real component of -3, an imaginary component of 4, and it does kind of double this angle from here and then to here. It is further away because we do multiply the modulus whenever we square or raise to any power a complex number. And so here the modulus, it looks like that's √5. I'm doing like root of 1 plus 4. And so the modulus of √5 times √5 produces something that has a distance of 5 from the origin. This would create a 3, 4, 5 triangle. So to generalize though, let's see, we could basically pick some value of b, and we could actually pick whatever value of b we want for now. Let's just pick 2, I guess. And if I wanted to find the modulus of this complex number, I would probably need to use arctangent, I think, because doing arctangent of opposite over adjacent would give me this angle here in this right triangle. But instead of 2, I think I'll just use b to represent that I could still kind of increase or decrease this spot, and this angle could change, because I'm not really sure what value b should be just yet. Dividing by 1 doesn't really do much, so arctangent of b is exactly equal to this angle from the x-axis to this complex number. And then after raising it to the power of 4, basically this will just add the angle 4 times over, or multiply by 4. We could do the same thing for the other point over here. The opposite side is still b. The adjacent side is now -1. So opposite over adjacent is b over -1, which is just -b. And this value right here is the resulting argument after raising that complex number to the power of 4. And as you can see, as we scale around our value of b, essentially these two numbers are identical, just they're different by a negative sign. And so the only time that these two values will actually be equal, so that the argument is the same after raising these two numbers to the power of 4, is if b is 0. This is the only time that we will find these values to be exactly equal. Fortunately, this spot represents one of the solutions we already found. This is 3, 0, or the real component is 3, and the imaginary component is 0. And this is the first solution that we found on the whiteboard. So now we need to think, how else could we find solutions in this format besides this one? And we do need to think about coterminal angles for a sec, because it's totally possible that the angle of 0 is the same thing as the angle of like 360 degrees or 2 pi when we rotate fully around the circle. So we will find two other solutions when these two angles are 2 pi apart, or maybe 4 pi apart, or 6 pi. Because if we just add 2 pi to either of these, or subtract 2 pi from either of these, we will find some kind of coterminal angles. And now I'm going to be looking around for when these two values are equal to each other. Okay, clearly this one's growing and that one's shrinking, so maybe I need to go in the other direction. And it looks like I passed over some kind of solution right around there. And what do you know? That's when b is -1. And both of these angles are at pi. So both of the resulting complex numbers, after raising them to the power of 4, will have an argument of pi. And so both of them will be roughly or exactly here on the negative real axis. And so this black dot represents the complex number 3 minus I. That's one of the solutions we found. And then if I just put a -2 pi here, then b would need to be +1. These two things match. And then this represents that 3 plus I that we found. And then one more thing, I did say that maybe we could totally just add like 4 pi or subtract 4 pi, or add 6 pi and subtract 6 pi. And that is true. Those would find more coterminal angles. So just to show you here, this intersection point also represents our answer. This 1 right here is the same thing as b being 1 right there. But if I try subtracting 4 pi to find another pair of coterminal angles, you'll see on these graphs that they never really intersect anywhere. And so this shows me that I won't actually find any like coterminal angle pair when these two values are 4 pi apart. Same thing if I add, we're not going to find any intersection points. And those intersection points are what we needed to find other solutions to this problem. So this -1 represents, again, that imaginary component being -1 there. This value being +1 represents that this b could also have been a +1, so 3 plus I. And then if we just get rid of this, then we can also see that just 3 with no imaginary component is also another valid solution to this problem. So that's kind of how you could think about it, like graphically, geometrically, with de Moivre's theorem. And essentially, we still do get those same 3 answers, and then we need to square them all and add them all up. We'd still get 25. So I think that's my whole solution today. I just wanted to talk a little bit about thinking about it in a different way before I finish the video. So I think we're all done. Thanks for watching. I'll see you tomorrow.